Good morning and welcome to lecture number 5 of this course on advanced hydrology. In the last class, we looked at the overview of the derivation of the Reynolds transport theorem. Then we looked at the deduction of continuity equation from the Reynolds transport theorem and also the momentum equation. Then we moved on to the integral form of the continuity equation, and we wrote down for volumetric continuity equation how the form would be. After that, we said that most of the hydrologic variables are discrete in nature. So, we need these basic laws of physics on the discrete time domain. So, we wrote the continuity equation in the discrete time domain. It is called the discrete continuity equation. Then we looked at two different types of data representation. First one was the sample data representation and the second one was the pulse data representation. Then we moved on and we looked at, or we started looking at one example of momentum equation. This was on a 60-degree elbow. So, what we will do is we will start with that example. When we closed in the last class, we had said that you should try to attempt or try to solve or at least think about how that problem can be done. I am sure some of you may have tried to do that, and some of you would have been successful and some others may not have been successful. So, we will start with the solution of that elbow problem today. So, if we define the problem once again, we are looking at a 60-degree elbow like this. We draw the control volume, which is the dashed line, and that is right next to the elbow. This elbow is nothing but a pipe fitting. So, there is pressure 1 acting on this side, there is pressure 2 acting on this side. The velocity here is V1 at the inlet. So, this is the direction of flow, goes like this. This is the center line of the elbow, and we said that it is a 60-degree elbow. So, this angle theta is 60 degrees, and the velocity here comes out perpendicular to the cross section here is V2. And then we say that we assume some coordinate system. This is x and y. This is our cross section 1, and if we take the second cross section, which is perpendicular to the velocity of flow. The data that are given are the discharge is equal to 1 meter cube per second, which is steady state. That is to say that a discharge is flowing at velocity V1 at cross section A and V2 at cross section 2, and it is a steady state. The values of the pressure or the gauge pressure at cross section 1 and 2 are given to us or known to us. 0.1 millipascal is 0.1 times 10 to the power 6 pascals. P2G is given as 0.09 millipascals, which is this much. Also given to us is the area of cross section as 0.1 square meters, and the same at cross section 2 is 0.07 square meters. So, these are all the data that are given to us. Also given is neglect the weight of water. Okay. Neglecting the weight of the water, what you have to find is the resultant force on the elbow. So, this is the problem statement. What we do in this case is we make some assumption about the control volume, and then we write down the expressions, or we draw what is called a free body diagram, in which we mark all the forces or the predominant forces which are acting on that control volume. All right. Forces are vectors, so we will take the components of the forces in the x and y directions in this case. So, we write all of them, and then what we do is we use our Reynolds transport theorem for the steady state case, which we have just written. So, what we will do is we will start with the Reynolds transport theorem, momentum component of that in x and y directions, and then we try to find out how much is the force acting on the control volume in x and y directions. Once we have that, we can find out the resultant force, magnitude as well as the direction. Okay. So, this is the force which is acting on the control volume. Now, the control volume will exert an equal and opposite force on the elbow, right. So, the force on the elbow will be just equal and opposite to what we find out. All right. So, let us get started, and first write your momentum equation, which is summation f, the left hand side is equal to the first component is time rate of change of extensive property stored within the control volume, which is triple integral beta is v rho dv plus the momentum flowing across all the control surface is beta rho v dot dA. We say that this problem is steady state, that is why this first component will be equal to 0. So, what remains with us is this summation f, or the net forces that are acting on the control volume should be equal to the net outflux of momentum flowing across all the control surface in this domain, which is this. Okay. So, then what we do is we need to find out what will be the velocities at the two cross sections. What we do first is we use the continuity equation on this control volume, which says that q is equal to a1 v1 is equal to a2 v2. I am sure all of you know this. So, that will give us v1 as q over a1, which is 1 over a1 is 0.1, and that will be 10 meters per second. Okay. All these data are given to us, and similarly v2 would be your q over a2, which is 1 over a2 is let me see 0.07. So, it will come out to be approximately 14.3 meters per second. So, we have the velocity components. Now, these velocities are acting perpendicular to the cross section, cross sections 1 and 2. All right. Now, what we do is we apply the momentum equation in x and y directions, momentum equation. And before we do that, we say that we let the force that is acting on the control volume in x direction is, let us say, Fx, and similarly we say that the force acting on the CV in the y direction is Fy. Okay. So, we will account for these forces on the left hand side of this Reynolds transport theorem or our momentum equation. Okay. And once we have done that, then your will come to the computation little later. The resultant, but the magnitude of these two components Fx square plus Fy square, and tan theta or the direction will be equal to f of y over Fx. Okay. So, if we are able to find this Fx and Fy, we would be able to find the force that is acting on the control volume, and equal and opposite force would be the force acting on the elbow. So, let us try to find these things. Now, what we will do is we will assume that the pressure force or the atmospheric pressure is acting equally in all directions. All right. So, that will cancel out. All right. So, basically what that mean is we just need to consider the gauge pressures which are given to us, okay, as far as the pressure forces are concerned. Okay. So, let us write then x direction momentum balance. Or we write the momentum equation in the x direction. Okay. So, let us say the Fx was the force acting on the control volume in x direction. What are the other forces acting? If you look at your diagram, you have pressure force. Okay. So, this is the pressure and it is acting over an area of A1. Okay. So, if you look at your diagram, this is parallel to the x direction. All right. So, this is P1G A1. What about the pressure force in the y direction? If you see that it is at the cross section 2 is not acting in the y direction, but it is acting at certain angle. All right. So, what we do is we take the component of that pressure force in the y direction. All right. So, that you can see easily would be P2 gauge times A2 and its component will be cos theta in the y direction. Now, this whole thing should be equal to, let me first write it, across the control surface of your V times rho times V dot dA. This whole term at inlet and outlet, okay, or at cross section 1 and cross section 2. So, if we did that, we write this is going to be rho times V1. I am taking the rho out and the velocity of flow at cross section 1 is V1. All right. So, this is V1 times V dot dA at cross section 1. All right. And what is the V dot dA at cross section 1? It is nothing but V1 times A1. We are taking the velocity, all right, same or the mean velocity at cross section 1, and we have said that we take the influx always negative. All right. So, we put a negative sign in front and then you have plus at the outlet you have the velocity in the y direction. All right. Now, you see that velocity is going down at an angle, all right, at certain angle. So, if we take its component in the y direction, the cos theta will get involved. So, you have the velocity itself is V2 cos theta, okay, and then the flux term will be V dot dA, that is velocity V2 times A2, okay, and this we can write as rho times V1 if we take outside, then we will have minus V1 A1 plus V2 cos theta times this V2 A2 is basically you can write as V1 A1 from the continuity equation, and V1 we have taken out. So, it is A1. Okay. So, either we can do that or we can put all the values of V1, V2, A1, A2, everything is known in this equation. Okay. All right. So, let us then write what will be f of x from this equation. Okay. So, it is going to be, you are taking the things on the right hand side. So, you have 0.09 10 to the power 6. What is this? This is nothing but P2G, this is given to us, times A2 which is 0.07, and then you have cos 60, that is V2, the component of V2 in the y direction, minus 0.1 10 to the power 6, this is your P1 G, and times area is 0.1, which is in square meters, which is A1. Okay. I am sorry, this one is not V2, this is A2. Okay. So, if you look at this equation, P2 A2 cos theta and P1 A1 we have taken on the right hand side. So, this is the pressure force terms. Okay. And similarly, we can write the other things, which is going to be plus you have rho of water is, let us say 1000 times V1 we had found out as 10 meters per second is outside, and then you have minus V1 A1, which is 10 times A1 is 0.1 square meters plus V2 was 14.3 meters per second. So, we have V2 and cos of 60 degrees, all right, and then you have A1, which is 0.1. Okay. So, we have done is we have plugged in all the values that are known to us in terms of the pressures, the velocities and the areas in this momentum equation, and after that we can solve it. So, what we will be able to find then is Fx is equal to minus 9700 newtons. Okay. Similarly, we write this equation in the y direction or the y direction momentum. Okay, in which your force acting on the CV is Fy. What is the component of the pressure force acting in the y direction? It will be P2G A2 sin theta. Okay, so it should be very easy to see for you, and equal to the flux term in the y direction. So, it would be, I will write it directly, minus V2 sin theta times V2 A2. Okay. So, you see that there is no term on the right hand side which involves V1. Why is that? It is because the velocity V1 is parallel to the x direction, all right. So, its component in the y direction will be 0. So, nothing gets contributed to the momentum flux in y direction due to flow in the x direction at cross section 1. Okay. It is important to understand that, and then only component we have is from the y direction, all right, and the velocity of flow is in the outward direction. Our direction or positive y direction is in the vertical direction, that is why we take this sign as negative. So, this term is negative because of the direction of flow, and you should not get confused that why the outflux of the momentum is taken as negative. It is the velocity which is acting in the negative y direction, it is because of that, and this component is V dot dA, simply V2 A2. Okay. So, once we have understood that, all that is needed then is to plug all these values. Okay. So, we can write down your f of y is equal to, it will be minus 0.09 times 10 to the power 6 times 0.07 sin 60 degree. Easy to see that this is your P2 gauge, this is your A2, all right, and then you have minus rho is 1000, and then you have velocity V2 which is 14.3 and sine of 60 multiplied by V2 A2 which is 14.3 times 0.07. Okay. You can simplify this, and then what we will get is the component of force acting on the control volume in the y direction as minus of 17,840 newtons. Okay. we have Fx and Fy. So, we can say that the force that is acting is Fx I in the vector notation plus F of y j, and you know how to find the magnitude and direction of any vector. Okay, I have written those equations down. So, I am not going to do that. Simply you can say that the magnitude would be square root of your 9700 square plus 17840 square, and theta would be tan inverse of 17840 over 9700. Okay, you can find out these numbers. I am not going to do that. So, this way we see that the application of the momentum equation to a practical problem of finding a force on the elbow. All right. What we just found is the force acting on the CV, and we will take the force acting on the elbow just equal and opposite of that. So, this way we can analyze the simple application or simple problems of momentum, finding force, finding areas and so on. Okay. Let us move on, and the next thing we are going to look at is another example which is also application of your momentum equation, and we are going to use it for a case of open channel. Okay. So, it is not only the momentum, but it will involve all the three equations. So, we are looking at one dimensional steady uniform flow in open channel. Okay. That is what we are going to look at next. So, this is the channel bed, and then you have, let us say, the water surface elevation in the channel is represented by this. This is your cross section 1, this is your cross section 2, and then you have the energy head, which is V square by 2 g, and okay. So, if we represent everything, let us say this is the slope of the channel is S0, this is the depth of flow at cross section 1 is y1, the depth of flow at cross section 2 is y2, and let us say this is the datum which is horizontal, or it can be actually at some any other location. Okay. So, it may be down there as well. So, this is your Z1, the datum head, and this is Z2. Okay. And this is the velocity head, which is V2 square over 2g. You all are familiar with that, and this is V1 square over 2g. And what is this? This is called the head loss or HF term. Okay. So, what we are doing is we are trying to analyze the situation wherein we have a one dimensional steady flow or uniform flow taking place in an open channel. So, what we will do is we will apply all the three equations and try to analyze the situation, that is continuity equation, momentum equation, and also the energy equation in the form of Bernoulli. Okay. So, if we apply the continuity equation, which we have derived in the form of this. Okay. And let me also point out that the velocity here is V1 and the velocity at cross section 2 is V2. The area of cross section is here A1 and the area of cross section here is A2. Okay. So, if we take the continuity equation, and because of the things are being steady, so this term will be 0. All right. So, what will that involve or tell us? That your inflow is equal to outflow, or if let us say if the inflow was q1 and outflow was q2, all of that we say is equal to q. All right. Now, we said that the flow is uniform. Uniform flow means that the velocities are same. All right. So, it does not change with respect to space. So, we say your V1 is equal to V2. What does that mean? That means your area of cross section at 1 will be Q over V1 and area of cross section 2 will be Q over V2. Okay. Now, if let us say assume this is a rectangular channel with the same width, it would mean that A1 is equal to A2. Why? Because A1 is equal to Q by V1 and A2 is equal to Q by V2 and V1 is equal to V2. So, both of these quantities are same. So, that means your Y1 is also equal to Y2. So, what does that tell us? That is, if the flow is uniform, then the velocities are same with respect to space, that is cross section 1 and cross section 2, and also the depth of flow is same, that is Y1 is equal to Y2. The next thing we are going to look at is the energy equation. Right? It is not the energy equation in terms of the heat energy, but it is more of the potential, kinetic, and the pressure head. Right? So, as all of you know, the energy equation is represented by this Bernoulli equation in this case. Z is the potential head, Y is the pressure head, and V1 square by 2G is your kinetic energy, and then you have Z2 plus Y2 plus V2 square by 2G. All right. At cross section 2 there is some loss, and which is due to the friction and other eddies. We call that HFF. Okay. That is, your HF is the head loss due to friction per unit weight of water, in this case the fluid. Okay. All right. So, we apply this energy equation knowing what are the values of different variables. Now, we have the uniform flow we just saw. An application of the continuity equation for the uniform flow, we have just found out that Y1 should be equal to Y2 and also V1 was equal to V2. Okay. So, we put these things, these two quantities into this equation. All right. So, Y1 will cancel out with Y2 and this quantity will cancel out with this quantity. Okay. So, that would simply mean that your HFF is equal to what? Z1 minus Z2. Okay. Next thing what you do is you divide this equation by, let us say the reach length is L on both sides. Okay. Then what is HF by L and what is change in the bottom elevations divided by L. Okay. That means your S naught, which is the bed slope of the channel, is nothing but HF by L, which is S of F for the friction slope, which we know already from our knowledge of open channel flow. Okay, for this kind of situation. So, this is how we derive this concept for a uniform flowing channel, that the bed slope is equal to the friction slope for uniform flow. Normally, for small thetas, that is maybe theta less than 10 degrees, we assume tan theta is equal to sin theta is equal to, theta sometimes is equal to SO is equal to SF in this case. Okay. So, whatever is your angle, if it is small, then we can take them all equal to the same thing. So, this is as far as the application of the energy and continuity equation. What we are going to do next is apply the momentum equation to this flow concept of one dimensional flow to the uniform flow in channel. Okay, so let us look at the momentum equation then for this particular case of one dimensional steady uniform flow in open channel. And we had seen yesterday that for steady and uniform flow, what is the momentum equation or the reduced form of the Reynolds transport theorem? It is nothing but summation f is equal to 0. Both the terms or both the components on the right hand side are equal to 0. Okay. So, what we do then is we look at the predominant forces which are acting on this control volume. All right. So, we take a reach of length L of the channel and then we draw the control volume, which is the water surface elevation, the cross sectional areas and the bed. Okay. What are the major forces which are acting on this? Okay. So, if you think about the situation, we should be able to find that there are three forces or three main forces acting. What are those? One is the pressure force, other is the weight force or the gravitational force, and the third one is the friction or the resistance force, all right, or the viscous forces. All right. So, if we see, let me first write it. You have the pressure forces acting on the control volume, then you have the frictional forces, okay, and the gravity forces. Okay. So, what we do is we will write the component of these forces in the x direction. Remember, it is a one dimensional flow. So, our x direction is the direction of flow. All right. So, we will be writing all these forces only in that direction. Okay. So, moving on. So, if we take, let us say this is a channel, all right, it has certain depth of flow and the cross sectional area is A, and let us say this whole quantity, what do we call this? This is your wetted perimeter P. Okay. So, if we write, let us look at each of these forces one by one. What are the pressure forces acting on this? We have a depth of flow y1 on the input cross section and we have a depth of flow y2 and both of them are equal. So, the pressure forces will be equal and opposite, that is P1A1 and P2A2, and P1 will be equal to P2. So, the pressure forces are equal and opposite on the control surface, equal and opposite, and they cancel out. So, we do not even need to worry about the pressure forces in this case. What about the frictional forces? All right. So, if you have this bed channel and this is your water surface elevation, the frictional forces are the resistance to flow due to these bed and sides of the channel. Okay. The bed and the side of the channel will resist the flow of water in the channel. All right. Due to that, you have the frictional forces which is acting in the opposite direction to the direction of flow. So, that is why this is, let us say, your f of f. Okay. What is the magnitude of, let us say, this frictional forces? Okay. From our knowledge of the open channel flow hydraulics, we will write this as negative of tau 0 P L, okay, where your tau 0 is equal to the wall shear stress, okay, or it is the shear stress which is causing the resistance to flow, that is force per unit of area, and the area on which it is acting is nothing but the P times L. P is the wetted perimeter and L is the length of the flow in question. All right. So, what is P is the wetted perimeter. It will be in the length units, and L is of course the length of the channel which is under consideration. Okay. So, this is what it is going to be. We will leave it at that, and then we move on to the gravity forces. Right. The gravity forces is acting in vertically downward direction. So, the whole weight of the control volume or the fluid or the water that is contained in the control volume, that is acting in the downward direction, but we need to take its component in the direction of flow, which is your x direction. All right. So, let us say that your f of g is the component of weight of the water in x direction. What will that be? It should be easy to see that it will be gamma AL. Gamma AL is the volume, all right, area of cross section times length. Gamma is the specific weight of water, all right. So, that is the weight, and then its component in the x direction will be sin theta. Should be easy to see for you. Okay. So, now what we do is we put these things in the momentum equation. All right. So, that will give us minus tau 0 PL plus gamma AL sin of theta is equal to 0. Okay. And all of you should be able to find this tau easily. What is tau 0? Will be equal to gamma AL. For sin theta we can write as 0 and divided by PL, and what is A by P? L will cancel out, of course. A by P is the hydraulic radius R. So, we have tau 0 is equal to gamma R S 0. Okay. And for uniform flow it will be gamma R S F. Okay. Okay. Where gamma is the specific weight of the fluid, which is water in this case, and R is the hydraulic radius, which all of you know is defined as cross sectional area divided by the wetted perimeter. Okay. So, what we have done now is that we have derived the momentum equation applicable to the one dimensional flow which is steady and uniform in an open channel. Right. So, what is the momentum equation? Tau 0 is equal to gamma RS. Okay. What we will do next is we will try to extend this concept to groundwater flow, and we will derive one of the basic equations which is called the Darcy's law, which is very predominantly used in hydrology for analyzing the groundwater flow situations in the saturated zone. Okay. So, let us look at the porous medium flow situation. All right. And what we will do is we will try to apply this momentum equation. All right. Okay. What is happening in the groundwater is you have the soil matrix and there are certain voids. All right. And what we assume there is that the water is flowing through these voids by what is called these tiny conduits or pipes which are formed due to the voids in the soil. So, what we will do is we say that the porous medium flow or flow through saturated portion of earth, right, we will say, let us say, is equivalent to pipe flow of diameter d. All right. Let us say that is equivalent to the channel flow which we have just derived, okay, for which we have said that tau 0 is equal to gamma Rs. Okay. For this pipe flow, the hydraulic radius, it should be easy to see for you all, is will be equal to d by 4. I will not derive that, you can do that easily. Okay. Now, for laminar flow in a circular conduit, the wall shear stress is given by this equation. Okay. We will take this from our knowledge of fluid mechanics. I do not expect you to remember this, but we will take this expression from our fluid mechanics. Okay. Tau 0 is equal to 8 mu v over d, where what is mu is the dynamic viscosity of the fluid, okay, and v is the velocity of flow and d is the diameter we have already defined. Okay. Now, what we do is, if we compare these two expressions, let us say this and this, and we also put r into this and combine all this, it should be easy to see that the expression for velocity will come out as this, gamma d square over 32 mu times SF. Okay. Does this equation sound familiar to some of you? Okay. Maybe it does not, but if I tell you that this whole expression, if I say that this is some constant that depends upon the property of the fluid as well as the soil matrix in the saturated zone of R, okay, and let us denote this as K, and you know that this K is nothing but the permeability or the hydraulic conductivity of the. So, if we did that, then we have V is equal to K times SF. In the groundwater flow, the whole of the cross sectional area is not available for flow. So, what we do is we say that this is Q over A, and we say that this is what is called the Darcy's flux Q, all right, and this is nothing but we say is the Darcy's flux, all right. So, that is to say your Q is equal to K times SF, where SF is the friction slope, or in other words we say Q is equal to K I, and I is the hydraulic gradient. Okay. This is the form in which most of you may have seen this Darcy's law. Okay. So, you see that the Darcy's law is nothing but the momentum equation applied to a simplified situation of groundwater flow in the saturated zone. An important aspect which needs to be remembered in the groundwater flow situation is that when the water is flowing through the pores, the whole of the area is not available for flow, all right. That is why the actual velocity of flow is equal to Q divided by eta, where eta is the porosity of the soil, right. So, if you have to find the actual velocity of flow of water through a soil matrix, then you find the Darcy's flux, and then you need to divide it by the porosity of the soil, which will be slightly higher than what you find as the Darcy's flux. So, that will give you the actual velocity, which is used in finding out the travel times of tracers and lot of this mathematical modeling and management of the aquifers. So, we will not go into the details of those, but this is the application of momentum equation to groundwater flow and one dimensional flow to the channel. That is what we have seen. Now, what we will do is we will move on and look at quickly what is called the energy balance or energy equation. Okay. When we apply our Reynolds transport theorem and we try to derive the energy equation, and we say that the extensive property is the energy, and this will be equal to the sum of three different types of energies. You have internal energy, plus your kinetic energy, which is half mv square, plus the potential energy, which is, let us say, mgh or mgz. Okay. So, this is your capital B and small b or beta, or the intensive energy corresponding to that, and let me say that this is some capital E, all right, or EU in fact. Okay. So, it would be, let us say, small EU plus half v square plus g times z, all right. So, what you do is you have divided this whole equation by the mass of the fluid. So, this is EU by m will be equal to small eu, which is the internal energy per unit mass of your fluid, and similarly this is your kinetic energy per unit mass of fluid, and this is your potential energy per unit mass of the fluid. Okay. Now, what we do is the left hand side of your Reynolds transport theorem is the rate of change of the total energy of the fluid. Okay. As we have seen in the case of law of conservation of mass and momentum, that the left hand side we account for a take care using some external law, all right. In this case, what we will do is we will write this as per the first law of thermodynamics. Okay. And again we will take this from our knowledge of the thermodynamics, we will not go into the details of that. And the first law of thermodynamics states that the rate of change of your total energy of a fluid is nothing but it is equal to dH over dt minus dW over dt, okay, where H is the heat transferred into the fluid during the motion, or in this case we have water in most of the cases, and W is the work done by the fluid on the system or the surroundings. Okay. So, we will take this this equation from the knowledge of our fluid mechanics. Okay. Once we have done that, then we write the Reynolds transport theorem as dH over dt minus dW over dt, that is the left hand side, that is dB over dt, is equal to, again, two components. First one is the time rate of change of extensive property stored within the control volume, this beta rho dV. Remember what is beta? This whole expression EU plus half v square plus gz rho dV. Okay. It is the time rate of change of extensive property stored within the control volume, which is d by dt of beta rho dV, and the second component is the outflux of the extensive property flowing across the control surface, which is beta rho v dot dA, and beta is again EU plus half v square plus gz times rho of your v dot dA. Okay. So, this is your energy equation for the fluid in terms of the total energy that it possesses. Okay. I will leave this internal energy at this point of time, and we will come back to this when we are looking at the evaporation. Okay. The next topic is on the transport processes. All right. Before I move on to that, let me look at different types of energies which are existent, and we will define this internal energy. Okay. We are all familiar with the kinetic energy and the potential energy, but this internal energy can be of two types. First one is the sensible heat, which is possessed by water, and other is the latent heat. Okay. The sensible heat is the is the energy which depends on the temperature, is that component which depends on temperature. All right, and latent heat is something which the fluid possesses without undergoing any changes in the temperature. All right, again the latent heat can be for the vaporization or for sublimation. Okay, and you may have seen this graph in your earlier classes, that if you try to plot the temperature versus the internal energy, okay, per unit volume with respect to minus 20 degree centigrade, what you have is something like this. Okay, this is your ice. All right, this is your liquid phase of water. Okay, and then you have the vapor here. Okay, what is this? This is the latent heat of vaporization, and this is your latent heat of fusion. Okay, and what is sublimation? It is the sum of all of these two things. Okay, so this way we see that there are different types of energies, sensible energy and latent heat, and we need to account for all these different types of energies when we are talking of this energy equation in this particular. How the heat transfer or the transfer of energy takes place, that is your transport processes. Okay, I would not like to go into the details of these transport processes. This would be more like a reading assignment for you. Okay, it's given in the book, and you are supposed to go through it on your own, except that I will say that there are three different ways in which the heat can be transported. All right, what are those? One is the conduction, other is the convection, and third one is the radiation. Okay, and I am sure all of you may have seen these three different modes of transport of heat. Okay, so you see that there are three different ways of transfer of heat, and there are certain equations which are associated with this. We will be needing this little later in this course, so I request you to kindly go through it. There are a couple of tables which describe the final equations in terms of the momentum transport, with similarity of the heat transport. Okay, at this point of time I would like to stop here and we complete this chapter, and in the next class we will start with the subsurface flow chapter. Okay.